Yes, good evening. It is going to 8 p.m. here. So today we are going to be talking about Doppler echocardiography theoretically. I've been showing you from different videos how Doppler echocardiography is done. I showed you two of them, that is color Doppler and the spectral Doppler. Spectral Doppler, remember, it was of two types, that is continuous wave Doppler and then pulsed wave Doppler. But what does Doppler mean? That is theoretically, because once you understand the theory, you'll be able to apply it practically, and then you make proper measurements. So today, as I've said, we are to talk about, what is this? Please write. We are to talk about Doppler echocardiography. We'll talk about Doppler echocardiography. That is today's topic. Theoretically, if you're interested in doing echo, you must understand this. If failure to understand it, a lot of measurements which are very critical will be poorly measured, and then a wrong diagnosis will be given. Just going back a bit, in your A level, for example, A level or high school advanced level of secondary education, those ones who did physics, if you did physics, you must have came across about Doppler effect, proposed by a guy, an Australian physicist called Ernest Wilhelm Doppler. Yes, this is a physicist, not a physician. This language is a physicist who found the Doppler effect, and therefore it was named after his name, Christian Doppler. What is the Doppler effect? Doppler effect is just a change in frequency. Change in frequency. We have, again, you remember that we used to draw these. We used to draw something like that. Something like that, and then you are here, the observer is here, you are there observing, and then this guy is going this side, this car is going that side. It has a siren, which produces sound. If this car is going away from you, the distance between the car and you will keep increasing. Whenever it keeps increasing and it is making your horn, it has a siren on. At first, when it is closer to you at this point, waves will be like that. Whenever it keeps, the distance between you and it keeps on increasing, something like this happens. So a car, a sound source, now we are using sound source, moving away from you. From the observer. And then you can have the sound source you are here, coming towards, it has a siren again. It emits sound waves. The siren is on, coming towards you. Sound waves will be moving in this. Whenever it comes to you, closer to you, it will keep on increasing like that. So what is this? Like sound waves, since electromagnetic waves, they move in this format. We have to understand this so far. So there is always a baseline. What did we call these ones? We call these ones crests, and then trough, compression, rarefaction. Compression, rarefaction. So from here up to here, this one is called wavelength. Just telling you this. I know you remember these ones. This is one wavelength. One wavelength, that is. So this full cycle is one wavelength. So if we have another wave, it is moving like this. Don't mind it. From here up to here, still it is one wavelength. It is one wavelength. This one, it is one wavelength, and this is one wavelength. So if the time from here up to here is 1 second, and also the time from here up to here is 1 second. So now I'm going to tell you what is frequency. The number of wavelengths per second is called frequency. So how many? If this is 1 second and this is 1 second, so how many wavelengths? 1, 2, 3, and 4. Hey, 4 and a half. So in this 1 second, there are 4. Frequency is 4.5 hertz. Then in this one we have 1, 2, 3, 4, 5, 6, and then probably 7. So here 7 hertz. In 1 second, for a particular sound, there is frequency is 4.5. That is, it is moving so many, like a few. But in this one, the second source of sound, it transmits sound waves of frequency 7. That is, in 1 second, the cycle repeats 7 times. Here, in the first instance, the sound wave that is emitted, the frequency, the cycle repeats 4.5 times per second. So which one has a longer wavelength? The faster one. The longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. So we go back to this analogy here. What is the wavelength? The distance traveled by a wave. That is, wavelength is just a distance traveled. For a car moving away from you, the distance that this sound wave from the source should move before it reaches your ear, it keeps on increasing. It keeps on increasing. For a car moving out from you, the distance, the sound waves from the source, in this instance, this moving car, which is moving away from you, keeps on increasing as far as the car is moving away from you. So, for this one, the wavelength will keep decreasing. It will start until when it fades. because remember again, from waves, this is the energy of the wave. That is the energy that is called amplitude. Yeah? The higher the amplitude, the stronger the energy. If the amplitude is weak, the wave dies. So the longer the wavelength, the lower the energy. For example, yeah, we can say the lower the energy. We shall see how, but the lower the energy. For this instance, when the car is moving away towards you, the distance the sound has to move, it is shorter. So it is compressed. So the sound wave is compressed, is compressed. So the wavelength keeps on shortening. So here it is shorter. Shorter wavelength, high frequency. Shorter wavelength, high frequency. Longer wavelength, low frequency. When the sound is moving away, the source is moving away from you, longer wavelength, low frequency. When the sound source is coming towards you, shorter wavelength, high frequency. This is what is happening, what we expected, Doppler effect. This is the so-called Doppler effect. Yeah, it is the Doppler effect. Like someone observed that whenever a speeding car with a siren on is moving towards you, the sound you keep on, the amplitude, the pitch increases. The pitch keeps on increasing, so you feel that, oh, the train is the other side, you still hear the siren is on, it's on. The more it comes closer to you, the higher the sound you get, that is pitch. When it bypasses you, the pitch keeps on reducing until when it fades, when it has gone so far away from you. Same thing, this phenomenon, we are going to apply it, we apply it in the heart. We are going to apply this one in the heart. How? Remember, in echocardiography, we defined the echo sometime back. That echo, they are reflected sound waves. In echo, remember we are using ultrasound. Ultrasound. We are using in echo ultrasound. So in ultrasound, again, we have a probe. We have our probe here. Ultrasound probe, it is the source of ultrasound. It produces ultrasound through the piezoelectric element, which is heated by electric current. It keeps on bending. Whenever it bends, ultrasound is produced. Now this ultrasound is projected in the tissues. This one can be abdominal scan. In the tissues. And this ultrasound, on its way, it finds so many interfaces. Depending on their density, you can reflect ultrasound, absorb ultrasound, or absorb, penetrate, or ultrasound can penetration if it continues, reflection if it goes back. Now, attenuation. When it dies, is not reflected, it is not penetrating, but it dies within the interface. Those are the effects that can happen with emitted ultrasound. This ultrasound, this probe, you may find it is labeled as 3, like AC3 to 8, for example. AC3, 8. It can be labeled like that. AC3, 8. What does this mean? It can indicate the frequency of the ultrasound it transmits. Like it can transmit frequency ultrasound waves of frequency 3 to 8 Hz. It can be like that. So this frequency, it is the one that is transmitted, and we always name it as F naught. F naught, transmitted frequency. Now, when it is reflected back, it is reflected with a frequency which is R, FR, for example, reflected, then transmitted. I've told you that ultrasound, once produced from a probe, it goes, depending on the density of the interfaces it finds, it can be reflected, penetrate, or absorbed. This one penetrate, like this one's absorbed, they are reflected. They are reflected with a different frequency from that of the transmitted ultrasound. So that's why I'm naming them as FR and F naught. So this one will always happen. Now, when we talk of whether abdominal ultrasound or echo, this one will always happen. This is a property of ultrasound. These people. It will always happen like that. So now when we talk of Doppler, now, I told you it is Doppler effect or Doppler shift. Doppler shift. Doppler effect or Doppler shift. That's how we are going to apply it here in echo. Doppler shift. We see the difference between the frequency of the transmitted ultrasound and the frequency of the reflected ultrasound, or transmitted frequency to reflected frequency. So this one means, again, we are getting the difference between F naught and FR. That's what we are looking for in Doppler shift. For example, if you transmitted F naught of 12 Hz, and then you get the reflected one of 5 Hz, the Doppler shift would be F naught minus, or FR minus F naught, and this one will be -7 Hz. Leave the negative, it indicates direction. Or if F naught is equal to 5 Hz and FR is equal to maybe 8 Hz, then Doppler shift would be FR minus F naught, we get 3 Hz positive. That one, it would be like that. So these two, one we are getting negative, another one we are getting positive. So remember when I was telling you this side that if the ultrasound source is moving away from the observer, the frequency decreases, and if the ultrasound, the source of sound is moving towards the observer, the frequency increases. Now let's go back to our echo. Who is the observer now? Remember, in echo, again, in echo, if we have our probe here, we have our probe. It transmits, and then it should receive. It transmits, it transmits, and then at the same time it should receive. Yeah, when this ultrasound goes, hits the boundary, it gets reflected. This is F naught transmitted, and then this one is FR reflected. So the ultrasound, the probe is our observer. It has two functions: to produce ultrasound and also receive the ultrasound. You can call it a transducer. It has a transducer inside. So send and receive. This is a function of the probe. It is our observer. So the observer is sending, at the same time is receiving, is waiting. This is, we can call this one a blood vessel. What is always in blood vessels? There is blood, the liquid part, and also the hematocrit part, which contains cells. In this case, red blood cells, RBCs. They are the ones moving inside there. They are biggest. They keep moving, yeah. So when this ultrasound comes and hits this red blood cell can be moving away or towards the probe, depending. This is a blood vessel. For this time, it is moving in this direction. Is this direction away or towards the probe? It is relatively away from the probe, because if you get a horizontal, a normal, it is moving away. If this is the y-axis, x-axis, it is moving away from the probe relatively. So since it is moving away from the probe, which is our observer, should the frequency increase or decrease? Reflected now, it is decreasing. It will be decreasing. Let me use a clear image here. We have a probe here. And then we have this blood vessel. This blood vessel is having some red blood cells. It is moving in this direction, this blood. So this one is producing ultrasound, penetrates, hits this red blood cell. And then, because it has hit a barrier, some were reflected here, but now it has hit a barrier and it gets reflected back to our observer. This is FR, and then this is F naught transmitted ultrasound. Since this red blood cell is moving away from the probe, FR will be less than F naught. And if we change that, this red blood cell were coming towards the probe, and then FR will be greater than F naught, because if it is coming towards the probe. So that is the Doppler shift, but it's not easy as that. It's not easy as that. You see, in echo, things are not like this, how we see them, yeah? This Doppler shift, it has an angle component. There is an angle component to this Doppler shift. Which angle? For example, this is a normal. The transmitted, for example, this is the red blood cell, and then this is our probe. We have the transmitted, it hits red cell, but now it hits it at what angle? We have this. There is an angle, this one, theta, that it hits. This angle is very, very important. Very, 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 very important. If we don't pay attention to this one, whatever we are measuring, it will be so incorrect or inaccurate. We are going to first pause it there. I've showed you a Doppler shift. I've showed you when we get a positive, or when reflected frequency be greater or lesser than the transmitted frequency. This is the transmitted frequency, and transmitted frequency is the frequency from the source. I've given you what is the Doppler shift, and then we are going to come up with I'm going to tell you more properties of sound, ultrasound. Remember, sound as a thing, it has so many properties. It has velocity, wavelength, and the frequency. It has these properties: velocity, wavelength, and frequency. They are related. Is it by this formula? Is it frequency? No. Frequency is equal to V. This is the formula. What? Yeah, this is the formula for frequency. This is how these three are related: frequency, velocity, and wavelength. So velocity of a frequency is V is equal to frequency times wavelength. This is the formula that relates them. You see here we have some kind of frequency, and here we've been talking about frequency. Even here we are talking about frequency. Wavelength, we have not talked much about wavelength, but it's there. Remember this. Remember this. You see, this is the formula for frequency. But also, there is speed of sound in air. It is a constant. Speed of sound in different media is constant. Now we are talking of soft tissue, because we are talking of echocardiography. Cardiography is through soft tissue, that is muscle, skin, blood, what? So the speed of sound in soft tissue, we are going to call it as C, is a constant at meters per second. We are going to relate these ones. So we have talked about frequency, velocity, and the constant here. Velocity and the constant here, and then wavelength, and then we have also talked about the Doppler shift. Yeah. So what we are going to do is to relate all these ones into one equation, because that's what we want. And then we see why do we do Doppler. We have Doppler shift. Yeah. Doppler shift. Remember, we said Doppler shift is a change in frequency. Doppler shift delta F is equal to we already gave it here, that is, see, FR minus F naught. Yeah, that is a Doppler shift. But we have another formula. We have another formula, which is Doppler shift is equal to 2 into F naught times velocity cos theta over 2. Oh, no, not 2. C, sorry, of C. This is also a Doppler shift, and it has whatever I've been telling you. I told you this about this theta, that is very important. And then I've told you about this V, where it is coming from, velocity. And then I've told you about Doppler shift, and then this cos theta, this angle theta here, we introduced a cosine of it. And then this 2, remember I've been telling you that transmitted and then reflected, you will not listen to anything unless it comes back to you. So what is the distance it has moved? It has moved the distance 2 and 4. 2 and 4. 1 plus 1 is 2. So these two journeys, the sound has to move. It goes, it comes back. It's like an echo. That's why we call it echocardiography. It is the one that is bringing this constant 2. Because it has to move, you must receive back. If you don't receive back, then that is attenuation. So this is equation 2. If we combine these ones, because all these ones are Doppler shifts, they are Doppler shifts, we shall get FR minus F naught equal to F naught into V into cos of theta times 2. So we want V. Why do we want V? I'll tell you. Now we shall get 2 into FR minus F naught over F naught into cos of theta equal to V. This is what is wrong with me. It is C, not 2. Sorry, it is C, not 2. C into, so this is equation 3. We have this equation 3. This is what we are measuring with Doppler shift. This one. With Doppler shift, we are measuring the velocity of whatever is moving. Now this time blood. This is why I even used red blood cells. So what is this? Cos of theta. If you can relate here, the Doppler shift, because I've told you this C is a constant from this equation 2. C is constant. F naught is always known. It is constant. That's why I was telling you here that the transducer can be labeled as 38. S38, meaning it transmits ultrasound of that frequency. It cannot change. So in these equations, F naught is constant, C is constant, 2 is also constant, V we don't know. We don't know V. And then theta changes, variable. You can put a probe, you can sight listen from any position. You can sight listen from position 1, you can sight listen from position 2, from position 3, from position 4, 5 and 6. So you can decide to put this probe For example, this was your position 1. You can decide to put it to position 2 so that it is like that. You can decide to put it here. Yeah, so that it transmits like that. So any position you choose. So if you put it here, this is the theta you're getting. If the position is position 3. If you put it here, the theta you're getting, it is almost parallel, so you are almost getting a theta of, at position 2, the theta is almost 0 degrees. If you put it here, this theta here, maybe here it is 80 degrees, here it may be around 30 degrees. So from different positions you put a probe, you decide to stand and listen from. Theta is going to change. The theta will change. Again, I'm repeating because this is very important. Theta will change depending on the positioning. If this is our blood vessel, we have blood cells inside, RBCs. If we decide to listen from here to put it exactly parallel, this is our transducer. And then we decide also to put it here. This is our transducer. And we decide to put it here. This is our transducer. This is position 1, 2, and 3. It transmits. Maybe here we have another red blood cell. They are compact. It transmits here. It transmits 1 here, and it transmits here. For this place, theta is 90 degrees. For this place, theta is maybe 50 degrees. For this place, theta is 0 degrees. So we are going to see, like we can confirm that in this equation, 2f0 into v into cos theta over c. Since these ones are constants, then v, Doppler shift, will depend on velocity, because velocity is not constant. The velocity we are looking for, v, is for velocity of blood. It is not constant, and theta is not constant. So Doppler shift will depend on velocity and the degree of cos theta. If we are to plug in the calculator, we want to confirm, we are to use a calculator, we see which one produces a bigger value here. This is a calculator I have. My first theta 1 is cos 90. Cos 90 is 0. So if, for example, here we take cos theta, we are going to have 3 scenarios. For theta equal to 90 degrees, Doppler shift will be 2 into f0 v cos theta over c, which cos theta is cos 90. Cos 90 is 0, so Doppler shift here will be 0. there won't be any Doppler shift. You won't record anything. When your angle, what is theta? Now I'm defining it fully. Theta is the angle of insonation or interrogation angle. Is 0. So if for theta is equal to 50 degrees, then Doppler shift will be equal to F naught into V into cos 50. What is cos 50? Cosine of 50 is 0.6. So it will be times 2, it will be 1.2856 F naught V. That will be the Doppler shift. For cos is equal to 0, yeah, for theta equal to 0 degrees, Doppler shift will equal to 2 F naught into V into cos of 0, that is of C, yeah, of C. It will be cos 0 is 1, cosine of 0 is 1, so it will be 2 F naught V of C. So this one, for cosine to be 0, the Doppler shift will be greatest when cos is 0. When theta is 0, Doppler shift will be greatest when theta is 0, and it will be 0 when theta is 90 degrees. That's why, when you remember in the other videos I posted, when I was actually recording, I was telling you we try to be as parallel as possible when we are trying to use Doppler. We try to be as parallel to the direction of blood flow as possible. Because of this reason, we have now seen the bigger the theta, the lower the Doppler shift. Yes. So that is the Doppler shift. That's why I was telling you that we have to be as parallel as possible. Yes. What else is remaining? Doppler shift finished. C finished. V. So why this formula here? Why this formula here? Because we don't know this V, and it's the one we are looking for. That's why we apply Doppler echo to look for this V. Why do we look for this V? We look for velocity of blood flow across the valves. Velocity of blood flow across the valves. So when you press pulse Doppler, continuous wave Doppler, this is what we are looking for. Theoretically, this is what we are looking for. The machine will calculate the theta, and it will give you the real velocity. As you remember what I did there in the other videos, I was showing you that now here we are going to measure, and it could be like this. It will be the baseline. I was telling you it is always having a baseline. For example, this is a spectral. This is, for example, flow through the aortic valve. If you put a cursor here, you measure, it will give you the velocity, maximum velocity. I will show you this one in the next video. Mean velocity, and then also pressure gradient. It will give you So when you put a cursor here after recording, maybe this one is continuous wave Doppler any, and you put here where it stops, you click enter, it will give you the velocities, not the Doppler shifts. It will give you the velocities. I've showed you how we relate velocity with the Doppler shift here. This is how we relate them. The course, the machine will know that this is your what. For it will just give you an answer. It will depend on you whether you have been as parallel as possible or not. For it will just give you, and then it will give you the C. You don't need to do these calculations, otherwise you won't know the FR, you won't know it. What we know is this is constant. F naught is also known. Course you won't measure, the machine will measure it. And then we shall record something like this. Once you measure, you will get these ones. And maybe next video I'll be showing you how actually to measure, what we call measure the chin, not the beard. Yes, thank you. Why we do Doppler equals to measure velocities, as I showed in this equation 3. Don't forget. Thank you so much. Very basic. Once you know it, you will be good. Yeah, I'm done.